Welcome back. In this lecture, I'm going to go through the difference between non-tumors and diastereomers. Okay, we said we were talking about isomers. Isomers are supposed to have the same chemical formula. Now, if there is a difference in connectivity, then in that case, we say we are dealing with the constitutional isomers. If the answer is no, there is no difference, we have the same connectivity. In that case, I'm going to ask, are we dealing with special isomers? Are we dealing with geometries that in a 3D, their 3D geometries are different? If the answer is correct, then I'm going to say I'm dealing with the stereoisomers. Okay, the stereoisomers, you can separate them to non-tumors or diastereomers. Non-tumors are mirror image of each other, but not superimposable. Okay, not superimposable, but they are mirror image of each other. Okay, so they are mirror image of each other, but not superimposable. If they are not mirror image of each other, and they are not superimposable, in that case, we say they are diastereomers. So diastereomers are not mirror image and not superimposable. And so they are not, again, not mirror image of each other. Okay, in this case, we have a double bond, and we said rotation around double bond is forbidden. We can't have rotation. I have a cis and trans isomer. Cis and trans isomers are stereoisomers. So I know I'm dealing with stereoisomers. That's one. Now, are they mirror image of each other? No, but they are isomers. They are, they are not mirror image of each other. They have the same chemical compound, the same formula, okay, chemical formula. And because they are not mirror image of each other, I'm going to call them diastereomers. Cis and trans always will be diastereomers. Okay, diastereomer. Forgive me, diastereomers. Okay. Now, the diastereomers have different physical properties, and of course, if you expose them to a chiral environment, they will be different. So, not only their, like their chemical behavior in the chiral environment, it will be different. Their physical properties are different. So, start with this: their physical properties are different. While in enantiomers, they have exactly same physical properties. Like boiling temperature for enantiomers, it will be the same, but not for diastereomers. In this case, we have a bunch of molecules, and as you see, the only difference between them is the wedges. That here, like for example, is pointing to us in the second molecule, and we drew them as like a dash line, so that means that they are back of the molecule. So if I assign the configuration for the first one, this is going to be R, and this is a clockwise, that one clockwise, and that's going to be counterclockwise. And because they change, they change position. They change actually the direction of the OH methyl and chloride, and the configuration from R it will turn to S, this one S, and S it will turn to R. So what's the relationship between 1 and 2? And you're going to say R turn to S, so R turn to S, and another R turn to S, and S turn to R. That means I'm dealing with enantiomers. So 1 and 2 are enantiomers. Enantiomers. But how about, for example, 2 and 3, or 1 and, let's say, 3? Let's look to this molecule. We're going to call this one number 3. And again, this one is gonna be R here. And how about this? This is gonna be 1, 2, 3 clockwise. Hydrogen is pointing to us because hydrogen is pointing to us. Okay, again, so we go 1, 2, okay, 1, 2, 3, okay, 1, 2, 3. That's supposed to be clockwise, counterclockwise, but because of H is facing to us, it will be R. Okay, so if I look 1 and 3, 1 and 3, 1 versus 3. Okay, 1, 3. We had R and S for 1. Okay, and how about 3? And 3, okay, we kept R, the first R, the second R, we kept it R, the third one, we turned it to R. Okay, we turned it to R. Okay, so one of them got mirrored. This one got mirrored, but the rest, they stayed the same. Okay, they stayed the same, but one of them got mirrored. Okay, if you have more than one stereocenter, and you can see that we have 3 stereocenters. So if you have more than one stereocenter, and like when you draw the molecule, and you can see that for example, one of the stereocenter did not flip, okay, or 2 or more did not flip. In that case, we say you're dealing with diastereomers. So 1 and 3 are diastereomers because at least I can see here 1 or 2, and clearly we have 2 stereocenters remain the same, while the third one got flipped, and so the third one and like the stereocenter turned to R, but because the rest they did not flip, I'm going to say this is a diastereomer. That's not an enantiomer. Enantiomer, all of them are supposed to flip. And as you see between 1 and 2, R and S, they got flipped to SSR. Okay, so let me practice some more example. Okay, this is the molecule that we have. Okay, let's name this molecule. I'm going to start labeling it from the left side, and I have 1, 2, 3, 4, 5, and this one, forgive me, this one will be 6. So I have 6 carbon, and I have a bromine on the second one. So I'm going to say 2. I'm going to say 2 bromine. Next, I have chloro on the third one, so I go 3 chloro. Next, on the second, fourth, I have a methyl, so I'm going to say 2. And 4, I have 2 methyl, so I go di. Methyl. Then I have 6 carbon, so this one will be hexane. Hexane. Now, how many stereocenters we have? Give it a try. And this is one of the stereocenters. Are you sure? No, that cannot be. Why it cannot be? Because you have methyl here and another methyl there. Those 2 methyls are identical. So number 2, it cannot be a stereocenter. How about number 3? Number 3 is attached to chlorine and 1 carbon here. That carbon has methyl and ethyl group. And that one is going to be the third substituent. And what's the fourth one? It will be hydrogen. So this is going to be stereocenter. And you can say the same thing for number 4. So I have 2 stereocenters. How many isomers I can have? Okay, I'm going to say 2 to the power of n, and n number of stereocenters. So I'm going to say 2 to the power of number of stereocenters. That's going to give me 4 isomers, 4 stereocenters. Okay, remember, first one, it can be R or S. Okay, R or S. And how about the second one? Second one also, it can be R or S. Combination of those, I can get 4 isomers. Both of them are R, both of them are S. So R, S, S. Or first one is R, the second one is S, or the first one is S, and the second one is R. I got 4 combinations. Sorry, 4 combinations I got. Now, listen carefully. I want to know the relationship between A and B. 1, A and C. 2, A and D. 3 until now. Okay. B and C, 4. B and D, 5. And C and D, 6. So I have 6 possibilities, and I want to compare the relationship between them. For example, what's the relationship between A and B, and A and C, or A and D? I'm going to list them. Okay. This is the molecule that we're talking about. We can have 3R, 4R, or 3S, 4S. And now check this. 3R turned to 3S, and 4R turned to 4S. Because we flipped the configuration, and so I'm going to say these 2 are enantiomer. Okay. Next, we had 3R turned to 3S, and then we had 4S turned to 4R. Again, those are enantiomers. Okay, so I have 2 sets of enantiomers until now. Okay, we said we can have 6 combinations. Let's go after those. Okay. How about, maybe I should take this one, write in a different page. I need more space, I think. And move this one also down. Okay. How about here? We had here, okay, R and R. Okay. We kept one of them. We kept it the same. We flipped only one of them. Only one of them got flipped. Okay. One of them got flipped. Again, only one of them got flipped, but those 2 remain the same. Okay. If you keep 2 of them the same, it doesn't matter which one. Okay, if you keep those 2 the same, and one of them got flipped, in that case, I'm going to say you are dealing with diastereomer. Okay, so diastereomers, one of the stereocenter will not flip. 4R remain 4R, and this is going to be the problem. Well, 3R turned to 3S. Okay, this one got flipped, but not the 4R. Okay, and you have the same story. Okay, same story for the next one. Next one, it will be also diastereomer. Okay, because 3R remain 3R, while 4R turn to 4S. So it will be diastereomer because the 3R remain 3R. Next one, we kept 4S the same. Here we kept the 3S the same. So those two are going to be diastereomers. And I'm going to call them diastereomer. So we got 1, 2, 3, 4 pairs of diastereomer, and 2 of them are enantiomers. We had 6 combinations, and out of those 6 combinations, I got 2 enantiomers and 4 diastereomers. Okay. Now let's name this compound. Okay. We want to name this compound. We said the name for it is going to be this. We named it before. I'm just going to copy paste this one. Okay. This is the name for it. So let's copy paste it. Okay, that's the name of the compound. You start from here. 1, 2, 3, 4, 5, 6. So it will be 2 bromo, 3 chloro, 2 and 4, 2 and 4 dimethyl hexane. Okay, that's the name of the compound. Next thing is I want to assign the configuration for each one. Okay, the configuration. You start with this. Okay, let me get rid of numbers. Okay, this is going to be number 1. Okay, next, which one is going to be number 2? This carbon is going to be number 2 because it's attached to bromine, and this one it will be number 3. Where is hydrogen? Back of the plane. Now, if you follow the numbers, this is a clockwise. So the first carbon is going to have R configuration. Okay, next carbon. Okay, if I zoom on it, it's attached to methyl. Hydrogen is back of the plane, so that's very good news. And which one is going to be number 1? Number 1, it will be this. This is number 1 because it's attached to chlorine. This is ethyl. Ethyl, it will be number 2, and methyl will be number 3, and hydrogen, of course, number 4. Okay, follow the numbers. If you follow the numbers, this is going to be counterclockwise. So this is going to be S. Okay. We got R on the third carbon, we got R. So for the third carbon, we got R, and fourth carbon, we got S configuration. So now you need to add something to the name and show configuration of each stereocenter. Okay, and you start with this. First carbon, the first stereocenter is the carbon number 3. Carbon number 3. And what's the second stereocenter? Carbon number 4. Okay, write the configuration for each. The third carbon, it has R configuration, and the fourth carbon, it has S configuration, and close it there. And this is going to be the full name of the compound. Last time, maybe 2-3 lectures before, I said if you have a mirror compound, even if it has a stereocenter, it will be achiral. Okay, it will be achiral. And as you see, for cis, because we have a mirror and the mirror is going to be there, this compound is not going to be active. So optically, it will be non-active. And because we have a mirror there. And how about the trans? Trans, you can't draw a mirror for it. So this one, it will be active. Well, cis, it will be non-active. Okay. And the next thing is we said, if you have an inversion center also will make the molecule not active. Okay. So for example, in this case, here we have a mirror. Okay. Do we have stereocenters? Yes, we have a stereocenter, and even we have a stereocenter, and molecule will be non-active. But we do have a stereocenter, so I'm going to say non-active or non-chiral. But because we have a stereocenters, okay, if you have a stereocenter, but the molecule, because of symmetry, is not active, the correct name for it will be meso. Okay, meso, whenever you have stereocenters, and because of symmetry, is not active. And you can draw the same thing here. Okay, we do have stereocenters. Those are the stereocenters, but because of the symmetry, those molecules are going to be meso. That means they are not active, even they have a stereocenter. And if you have inversion center, what will happen? Okay, inversion center is here. Inversion center is turning nitrogen to nitrogen, dimethyl to dimethyl, and nitrogen, oxygen to oxygen, or carbon to carbon. And the inversion center also will make the molecule not active. And so the inversion center here an inversion center made the molecule and not active, even you do have a chiral center there. So I see a chiral center here and another chiral center there, but still the molecule is not active because of the inversion center.